So welcome. It's a great pleasure to share with you some of our work, our recent work in the field of developing R&D tools for emerging displays, and OLED displays play a key role for us since many years. So um, Fluxim actually is a spin-off from Zurich University of Applied Science, and over the years we have developed many different tools. We see here the historic overview of our company, and actually our first product, Setfos, is now turning 20 years. It started in 2004, and then company was founded in 2006. Over the years, we've added not only simulation software like LAOS for large area modeling, but also PIOS is a measurement instrument for all-in-one characterization for DC, AC, and transient measurements, and then also Philos, an angular spectrometer, and Litos light stability testing equipment. Now, the outline for today, I try to span from devices all the way to display level, and I would also include some degradation, as I mentioned in the title, something about stress testing. So in the first part, I will talk about OLED devices themselves, how they are composed of the thin films, and uh, one aspect is the analysis of efficiency roll-off, which is still an aspect that is causing some challenges. For that, we actually have recently introduced a measurement technique that we call modulated PL spectroscopy, MPLS. And as I indicated, we have also one example today about OLED degradation analysis. And then slightly a topic not directly related to OLED, but since OLEDs are also being combined with QD films for blue OLED plus down conversion to red and green, we have actually put some effort into characterizing the down conversion films that can be combined with OLED. And so that's an additional topic. And finally, I give you an outlook on something that we started to develop, namely a calculation tool to calculate the display power consumption and to actually choose proper set of subpixels in order to have a reduced power consumption of the display. Now, the first topic, efficiency roll-off. After all these years, this is still an issue. Here's an older paper where you see phosphorescent OLED efficiency, how it reduces with increasing driving current. And there have been many mechanisms attributed to these phenomena, ranging from singlet annihilation to triplet annihilation, or also triplet polaron quenching, which is something we will discuss a bit closer today. Quite often, for describing these behaviors, one has used zero-dimensional rate equation models, which is good, gives good guidance. But however, we think it's better to go and actually resolve the OLED in its one-dimensional cross section, and to better understand where exactly is this roll-off coming from. Now, in that context, we and actually others, colleagues, Professor Holmes in the US has introduced a nice method looking at the PL efficiency, not only in the on state after turn on, but also below turn on. And he has observed, depending on the OLED materials used, so these are two different OLEDs. One of them shows a constant PL efficiency below turn on, and the other one has a polar ETL that gives rise to some charge accumulation on the other side of this interface. And that actually, this charge accumulation can lead to exciton quenching. And that is observed by this drop in PL efficiency below the voltage turn on. And for that measurement, of course, you need to excite the photoluminescence by optical excitation, but at the same time, there's a voltage scan happening, as this graph shows, from reverse to positive bias. A voltage is scanned, and that those carriers that are flowing or which are accumulated at interfaces do influence the photoluminescence efficiency. Now, we have tried to actually simulate this experiment where we want to take into account light absorption of the blue light that is trying to excite the photoluminescence. Then we solve the charge and exciton drift diffusion equation, so we can solve that in steady state or in transient, and we can, in steady state, for instance, here we can look at the profile of carriers and electrons and holes, and also where the excitons are, and if there's an overlap of excitons and holes, and if we allow for quenching between carriers and excitons, then we can actually indeed observe different exciton rates that are happening in parallel. So there's this blue area here, which is the one we want. We want to have radiative decay, but there's also a contribution, a loss mechanism of non-radiative decay, which is here in green. And you see here what we observe is that the drop in radiative output can be attributed to this yellow loss mechanism, and the yellow loss mechanism is introduced by um, hole quenching of the excitons. And now, indeed, we can reproduce, at least qualitatively, this curve here of the drop in PL efficiency below voltage turn on, as you can see here, and the origin of this loss in PL efficiency is coming from charge exciton quenching. Now, that was the model part, but we also tried to measure that basically with our commercial instruments, just slightly modifying the setup. So usually for electroluminescence, you have the contacts to the device. This is a bottom emission OLED configuration where we collect the light and we put it into a photomultiplier sensor. Now for PL measurement, we just add an LED at 365 nanometers and we excite same time as EL, and we do take advantage of a lock-in method. So we apply a modulated light pulse, and we then can analyze the PL signal without considering the EL part on the ambient light. And indeed, what we see here is the PL that is dropping below the turn on of the OLEDs. In the red curve is the electroluminescence turn on. So the proof of concept measurement works, and now the OLED that we investigated is actually this red emitting IRMDQ ACAC emitter, and we measured JV curves, we measured capacitance versus voltage, we measured current efficiency roll-off here versus device voltage, and in addition, as introduced just before, we measured the modulated PL spectroscopy data, which is PL versus device voltage. And with our drift diffusion and optics software SETFOS, we can reproduce all of these curves, and it turns out that capacitance, JV, and efficiency roll-off, yeah, you can find parameters to describe those, but it's not always unique set of model parameters, but the use of this additional experimental data set, the PL dependent on the voltage, this data set allows us to better nail down the parameters that are responsible for this drop off here. And we found that the triple polar quenching with holes is more severe than the one with electrons, and this can be seen in this graph up here, where the radiative decay rolls off here, and there are these two quenching phenomena, but in parallel, there's also the triplet annihilation that happens at very high driving levels. It gets more severe as we have an increase of the triplet density. So that's pretty nice additional experiment to add to the characterization set, and it helps to find the right model parameters. Now, I'm switching to degradation analysis of OLEDs. Here's an example data set on the right-hand side. This is a data set that can be obtained with our measurement instrument LITUS, which has 4 different chambers for different temperature, stage temperature, and then also different current driving levels. So in principle, one can analyze accelerated lifetime testing scaling laws. But today, I don't want to focus on that. I would rather try to understand in this particular OLED that was provided by Merck, fabricated by Merck, we want to understand degradation phenomena. So what we did is, while we stressed, we do an interruption and we do advanced characterization with pios. So the stressing is done with litos, but the systematic interruptions are done by pios, where we focus today on three measurement techniques: JVL, capacitance voltage, capacitance frequency. And you see on the right hand side that in the first 135 hours, the JV systematically drops, the current is being reduced, or in other words, the voltage is increased to achieve the same current, and the capacitance voltage curve shows also something systematic and something funny indeed, that there is a shift first to the left in the first hours and later to the right of this inflection point is moving around in a funny way. And in the last data set capacitance frequency, we see that the fresh device has a high capacitance, and as the device degrades, we have a low frequency capacitance that drops to a certain plateau here. Now, long story short, we actually were able to reproduce this interesting phenomena. So the first phenomena is this shift of this plateau to the left, um, which we are able to describe by introducing electron traps in the EML. And notice that the turn on voltage of this OLED is actually around 2.5 volts here. And the fact that below the turn on voltage, we already see significant capacitance increase. This is usually assigned to a polar layer in the OLED, but we had to introduce not only polar layer, but we had to introduce electron traps in order to describe this shift to the left here. So the electron traps are assumed to increase in density for the first 7 hours. That's the time scale of this arrow here. And the other effect in this first 7 hours is also that the hole traps in the HTL at that interface increase from 0 to this value here. And these two assumptions were needed to describe these observations. So the device simulation really helped to understand what's going on. Now, that was the main part about OLEDs, and now I briefly touch upon quantum dot down conversion foils or films that can be inkjet printed directly on OLED. So what we did here, we didn't have a QD film directly on the OLED, but we actually had a backlight unit based on a blue LED. So, but in general, you can think of using red emitting quantum dot films on top of micro LED or on top of OLEDs. But for our study here, we received down conversion films from a Korean company, InnoQD, that focuses on QD materials. And now to understand what's going on in the film, so there is blue light incident, and then there's scattering of light, and there's absorption of light and down conversion, and then again scattering of the down converted light. So all these phenomena can be described in our simulation software SETFAS. But in this study here, we wanted to check whether we can accurately determine the light down conversion efficiency, which we called LCE. And we used for this our angular luminescence spectrometer that is shown on the bottom here. We have a collecting fiber bundle that collects the light, and we have a rotating stage where this bundle of light, backlight, and film is rotating with respect to the fiber bundle. And the data you see here is first the characterization of the backlight unit, just the blue light itself, and then the combination of backlight unit plus QD film. And you see that now we observe this red emitting spectral peak here, which does drop as the viewing angle increases. And the actual angular dependence is here summarized for both the backlight unit itself and then for the bundle, where we can separately plot the intensity of the blue peak, this one, and the intensity of the red peak. And you see there's some very particular shape of the angular emission. First of all, the chosen backlight had this funny double peak angular dependence. The blue transmitted light has a rather flat emission, but then a drop. And interestingly, the down converted light has a lot of contribution for large viewing angles. And this has to be all taken into account to actually calculate the light conversion efficiency. And this is done in a post-processing step by integrating across this whole angular range that was measured. Of course, this is one way to do it. Another way is to use an integrating sphere, but there we lose a lot of valuable information, which we as modeling guys are interested in. So that's why we choose the angular measurement. And now we notice that the way we do the measurement really can influence the value of the light conversion efficiency. And we see two distinction of cases. So in one case, the spectrometer is sensing this spot size here, this square, but the excitation source is a planar light source, but we use a mask such that only a small illuminated area excites the QD film, and the measurement spot is larger than the excitation spot. That's case one. And the other case is where we have a large area illumination source, and that one is larger than the measurement spot. And what we found then is interesting dependence. So this is actually a calculation of the situation. We use the Laos simulation software, which has a 3D ray tracing solver included that includes me-scattering and down conversion mechanism. And we see that the case 2 actually leads to more signal in the detection arm in the spectrometer. And the reason, and you see it here in a spectrum, we have the blue peak of the excitation source that is transmitted partially, and then the red peak, which for case 2 is much stronger than for case 1, where the excitation spot was smaller than the detection spot. And in order to understand this, we ran the Laos ray tracing calculations, and we took care of the actual configuration of the geometry, the area of illumination, and we noticed that this dashed area is the measurement spot of the spectrometer to which this fiber bundle is sensitive to. And we are actually collecting light which is excited in case 2 by the large area illumination source. And this light is kind of laterally entering in our detection area. And this is why we have more red intensity in case 2. And this is actually simulation result here. And the measurement results were actually obtained in the following way here. We did again the case 1 and case 2 configuration, but in addition we also looked at the influence of different angular profiles of the backlight unit. So the double peak example what I shown before, but we can also modify the illumination lamp that is just in touch with the QD film to have a different angular intensity profile. And you see here on this result that the conversion efficiency for case 1, where the illumination area is small, we have a smaller value of the conversion efficiency. If the illumination area is larger, then the apparent conversion efficiency is overestimated, it's much larger. And it even depends on which profile of angular light source you use. So for this second angular profile, we have a slightly lower efficiency observed, and for the double peak angular profile of the light source, we even have a somewhat more lower efficiency determined. So this really shows us that it's gonna be rather delicate how you actually do this measurement. Now, last two slides here is the last topic that we have been working on recently, and where we presented some results on the topic of power consumption calculation, which is something that matters for the battery life of the mobile phone, the proper choice of subpixels, and there is a startup company in the UK called Exiton that has patented and introduced a concept of turbo OLED. And yeah, this is just a sketch on the left that it shows that we started 20 years ago with device level OLED stack simulation. In 2015, we started with large area display pixel array simulation, but now in the next year, we hope to start releasing this power consumption tool, and it should allow to analyze different concepts of pixel designs. So the new concept, turbo LED by company Exiton, is that instead of using 3 subpixels, using 6 subpixels for each of the 3 primary colors, use the light and the deep version. And the deep version is this large triangle in the color space for a chosen picture. Here's the Swiss Matterhorn. Yeah, you see that most of the pixels in the image are actually from a region in the color coordinate diagram, which is central here. So these are not really deep colors. So it allows us to use light subpixels, which are more efficient than the ones that are more deep colors. And this is a way to save energy, save power consumption. So another example picture was calculated to check the standard RGB pixel power consumption, and here the advanced concept of turbo OLED. And you see that here's much less intensity or power consumption occurring for the new choice of subpixels, up to 40% reduction. So this is an outlook what this calculation tool can be useful for. And this is a glance at the GUI, graphical user interface, of this display power consumption tool, which then can also import JVL data that is simulated with ZFOS. And in ZFOS, you can then look at more details of these primary RGB colors that are used for the subpixels. With this, I'm finished with my presentation. I realize slightly over time. And I touched on 4 topics: OLED efficiency roll-off, OLED degradation, QD down conversion analysis, and display power consumption. Thank you for your attention, and I would like to thank my colleagues, especially the ones mentioned in a yellow frame: Sandra Yanacha, R&D manager here, Baldassar Blil, product manager, and many more colleagues highlighted here that made these studies possible. Thank you for your attention, and please don't hesitate to get in touch with us.